Welcome, mindsetters, to this grade 11 session. And before we even get started with all that stuff, with the science, and we still have a lesson to do. But exactly, I'm going to hand over to Indiana, who's going to tell you what's happening right now, because I'm excited. I'm too excited to be explaining this. So
I know. Just calm down, Ty. Just calm down. Okay, so guys, what is happening right here? As you can see, we've got an extra guest, and if you were watching last week's Learn Extra Live science show, we hit 10,000, and this, my friends, is the 10,000th mindsetter. Marcel, how are you?
I'm fine, thanks. And all of you?
We're good, we're good. You're a bit nervous, hey, being in studio for the first time?
A little bit.
So is it everything you expected? Scary.
It's a lot different than I expected.
Okay, so guys, Marcel, we gave him a little giveaway, a little prize, and that we wanted to hand over on the show to you. Marcel, first of all, we want to know a little bit about you. What are your favorite subjects?
Geography and physical science. So.
Guys, and that's why we brought you in today.
Science, yeah. Perfect.
So guys, what grade are you in?
I'm in grade 11. I'm at your school, Dynamica.
Yeah, so guys, if any of Marcel's friends are watching, please let us know on the page and tell us. Yeah, I think it's amazing. And now we've got a grade 11 mindsetter in studio that loves physics, that will be sitting in with Bruce and Ty during this entire lesson. So if there are any questions you do want to send to him during the lesson, please do so on Facebook and on Twitter. But Marcel, here it is. Okay, so now this is your airtime. So you can SMS and Facebook and
all the good stuff.
Chat to us on Mindset Learn.
Exactly.
What we've also got in Marcel is grade 11 maths X sheets, which should help you with your studies. We've also given Learn Extra revision program, a set of DVDs.
Also, just thinking in advance, he also gets the grade 12 ones too. Yeah. So you'll be nice and properly prepared.
Yeah, we've got some maths textbooks. We do, exactly, like physical science, grade 12.
Even little notepads and more X sheets.
Physical science, grade 12. So you can see that we're thinking for you for ahead of time.
Exactly. Okay. So you'll be nicely proper prepared for your matric. And by the way, talking about matric, lady, he is available for pre-booking for matric dance. So just putting it out there, you know, just
number will go around there.
The number is going to be at the bottom of the screen.
Yeah. So Marcel, tell us just quickly before we get to the lesson. Will you be using Mindset Learn during grade 11, grade 12? What do you think of us using Facebook to talk to the learners? Is it working? Is it not working?
Okay, I'll definitely use Mindset. I've been using it this whole year, basically. I've used it in the past as well. And on Facebook, it's very helpful, especially the people helping each other around. It's like it's a family act, basically. They're helping each other there.
That's exactly. I think Marcel hits the nail on the head. That's what we are, guys. We're a community helping each other to learn more and learn extra. This page, our Facebook page, and this platform is not for us. It's for you guys to learn more and to learn extra. And without further ado, I think we're going to take a little break and get straight onto the physical science Learn Extra live lesson, grade 11.
Yeah, and we're going to try and figure out how to get all this stuff into Marcel's bag so he can take it home.
Exactly. I think we should have given him a bigger bag. Okay, guys. See you now after the break. Bye.
Welcome, mindsetters. I hope you've had a nice little break and you guys are ready. So Marcel and I are going to be winging for Mr. Bruce here. Mr. Bruce, we're good to go for the lesson?
Yeah, good to go, and good to have Marcel in the studio with us as well. And guys, what we're going to be looking at today is looking at chemical reactions. It's the last of the three types of chemical reactions, namely substitution, addition, and elimination reactions. Remember, we've covered our acid and base reactions and our redox reactions, and now we're going to finish off with substitution, addition, and elimination reactions. So I'll get ready for the lesson.
All right, awesome. So
great.
While you're walking that way, I'm going to tell the guys, make sure you get on the Facebook page, www.facebook.com/learn extra. And if you're friends with Marcel, yes, this guy, his face, remember it. Make sure you get on the page, get chatting to us, because he's also going to be chatting to you guys. So mindsetters, we're going to have some fun. Bruce, take it away.
Great. Thanks very much indeed, Ty. Well, guys, as I said in the intro, we're going to be having a look at our third and last type of grouping of chemical reactions for this particular course. And that's namely going to be our addition, substitution, and elimination type reactions. Okay, remember guys, over the last couple of weeks I was looking at acid-base reactions, and we looked at how we identified acid-base reactions. Last week we looked at redox reactions involving the transfer of electrons, and now we're going to be having a look at these particular type of reactions and looking at what makes these reactions quite unique. So what I'm going to have a look at, if we go to the board, you'll notice now that I'm going to start with looking at our an addition type reaction, or our addition type reactions. And the important thing is that these type of reactions occur when two or more reactants combine to form a final product. And the important thing is that what I've tried to show here, before we get into any of the complex chemistry or what might seem complex chemistry, is that we are taking a reactant A plus a reactant B, and we are adding them, we're combining them together to form one product, which we're going to call C in this particular type of general equation. So guys, it's always useful just to know and just to look at these general type of equations, because they help identify the pattern that these different types of reactions possibly take. Okay, so what we're going to have a look at, and I'll first put it here quite in a bit of detail. And what it means is that all the atoms that were present in the reactants will be found in the single product formed. So in other words, all the atoms from the reactants A and B will combine to form a product which is going to be C. Okay. In other words, if C is the final product, there will be no A or B remaining behind. Okay, so now what we need to do is actually have a look at the reaction itself. Now, you might look at that molecule or that compound, you might say, wow, this looks a little bit complicated, I'm not too sure what we've got here. But guys, I don't want you to worry about it, because I'm going to show you now the style of these type of reactions. These particular molecules or compounds you're going to, funny enough, come across in your grade 12 year when you look at the organic chemistry section, which is a really important section for your end of year finals. And you study it hard. It can be actually quite a simple section, although it might look a bit daunting at the moment. But these particular type of reactions actually give us a really good look at a particular style, and we're going to be looking at an addition style and how this actually works. So what I've got here is this molecule. You'll notice it's made up of carbon and hydrogens, and the important part is that we've got this double bond that exists between the two carbons. Now this double bond becomes important in this particular type of reaction, and I'm going to react it with a molecule of bromine, the diatomic bromine, and I've just given a little symbol over there. But guys, what I've got at the moment is a little model just to show you, and hopefully this will help you just a little bit when it comes to understanding this. So what I've tried to have a look at over here, and if the camera can pick this up, is that I've taken this little sphere, these spheres, and I've got these two black spheres here. They represent the carbon atoms, and these little white spheres that come off are representing the hydrogen atoms, just like I've got over here. And you'll notice now, if I turn it that way, you can see my double bond. I've got a bond at the bottom and a bond at the top, and that's how we actually have a look at it in our little molecule. Okay, so there's now just a molecular representation of what we got, and hopefully this might make life a little bit easier for you. If I now take bromine, okay, and there I've represented bromine, and can you see now bromine, the two bromine atoms joined together by a single bond, just like I've represented over there. What is going to happen? Well, guys, these are my two reactants. This is going to be reactant A, this is going to be reactant B. So what's going to happen? Well, in these type of reactions, you'll find that when we have a double bond between carbons, the double bond is able to break, and I'm going to just break the bond like that, okay? The bond is able to break, okay, leaving two exposed sites on that molecule. Same thing happens with the bromine. The bond breaks, leaving two bromine atoms, and what can happen now is that the one bromine can come in and add at this end, catch it, there we go. and the other bromine can come in on this end. And can you see now we've got a brand new compound? What have I actually done? By breaking the double bond, I have been able to add my bromine atoms from the bromine molecule to create a brand new substance. And that's going to be my product C. How do we represent that on a piece of paper? Well, very simple. We have a look at the board, and I scroll down. Can you see, guys, how I've represented it? There now are my bromines, and I'm just going to circle them like that. They're my bromine atoms that have now added. Notice the double bond has broken, okay? And therefore, I've got a brand new product. And that is what we call an addition type reaction. Okay, right, so if we go down, we can just summarize this by saying in this reaction, the double bond is broken, bromine atoms are added to each carbon where the double bond is attached, and a new compound is formed which has no residue atoms from the reactants. If I get my model again, can you see, guys, that we don't have any other residue atoms? Both bromine atoms have been used up in the addition reaction to form the new product, which is C, okay? And there it is, okay? So, whoops, what else can we have a chat about? Well, can you see now a different representation of putting it down? If I take my molecular formulas rather than my molecular structures, basically the molecular formula is C2H4 plus bromine gives us C2H4 and Br2. And can you see now, there, guys, is my bromine that's attached. I now make it part of my new molecule. We've got a brand new substance that has been formed. Okay. Now, what I've also put in here, and I thought this might be quite interesting for you, is to have a look at some uses of different addition type reactions. Where do we see some addition type reactions? Again, guys, don't worry about the molecular structures. Just rather worry about the mechanism, or consider the mechanism that we're actually having a look at, and it will make it very easy. But I thought this might be quite interesting, because if I take that particular molecule over there, and its actual name is ethene, okay, and I add it to water, you will notice now that the water molecule, okay, because remember, guys, water is made up of 1 oxygen to 2 hydrogen atoms joined like that. You will notice now that, whoops, let's get a different color here, that the OH part of the water is going to break away from that H part, and you will see now that the OH will join at one part. Remember, that double bond is going to break. There's the H joined on to the other carbon, the other position where the double bond was attached, and we now have got this product here, which is called ethanol. Okay, ethanol, you might have heard of, is basic alcohol. Okay, we use ethanol in a number of products, alcoholic beverages, that people over the age of 18 are able to purchase. Plus, they also use ethanol as additives in certain types of fuels as well. Okay, ethanol does have certain cleaning properties. It's also used as antiseptics and things like that. So there's quite a lot of uses for ethanol. But can you see now it can be made very simply through an addition type reaction. Okay. There now is the chemical formula, or the chemical equation, with the chemical formulas in the equation. C2H4 plus H2O gives me C2H5OH. There is the OH added, and notice, guys, that there are now 5 hydrogens instead of 4 there because of the addition of H2O. So, guys, there it is. A plus B will give me C. There is now my addition type reaction. Another example, and this one is also quite nice to have a look at, is making a margarine. Now, a lot of us eat margarine at home as a spread. We put it on bread, we put it on our bread rolls, and things like that. Some people even cook with margarine. Okay. Now, where does margarine come from? Well, it comes from an addition type reaction. And basically what it is the adding of hydrogen, okay, hydrogen gas, to vegetable oils which contain long carbon chains with double bonds. Okay, again, notice, guys, we have the same consistent story of a double bond being present in that particular molecule. So, how does it work? Well, what I've done here, and please notice I've used these little symbols R. They basically represent the long chains. Okay, so what I've done is sort of spliced out of the middle of a chain. I've spliced out a small portion showing a double bond. Okay, because remember, guys, vegetable oils, these chains are very, very, very long indeed. Okay, and all I'm doing is adding it to hydrogen. And can you see now? There's the double bond over here. There's the two sites where we can now add. There they are. The hydrogen breaks, so it's just like the bromine. The hydrogen will break, so we get the breaking of the bond like that, and the one hydrogen is able to go into that position, the other hydrogen is able to go into that position, and there we now have our addition of hydrogen. We call that a hydrogenation reaction. Again, something that you'll learn about in grade 12 when you do your organic chemistry section. But maybe just a good idea just to have a little bit of a practice, and you're ready. So when they start, your teachers at home or at your school start using those words, at least you can say, aha, I heard them first on Mindset Extra. Okay, and that, guys, is basically just our addition type reactions. I've rewritten it again in terms of a chemical equation. There is the little formula there. Notice, guys, there's my R's. I can just put them in like that. There's the addition of hydrogen. And can you see now that the number of H's have gone up by 1, which means we have added now to the molecule. And there we've got it. Time, Marcel, anything coming through on Facebook at this stage?
Not quite yet. Right now, we're just actually sifting through the mindsetters, just trying to pick up the right questions to kind of ask. So I think for now, it's good to go.
Are we good to go?
Yeah.
All right, so shall we carry on, and we can look at our second type reaction?
All right.
Okay, great. So hopefully, guys, that's got everyone sort of got the basic understanding of what an addition type reaction is. But now we're going to go to another reaction, which is called a substitution. Okay, now the word substitution should be something that we've done quite a bit of, and you've seen quite a bit. Think about a soccer team, okay? What actually happens sometimes in the first half, but almost certainly in the second half? One player goes off the field and another player comes and replaces him on the field. Okay, that is basically what we've got in terms of a substitution. So when we look at substitution in chemistry, what we're going to be doing is that we are going to be taking one particular atom or group of atoms off a molecule, and we're going to be replacing that with another type of atom or group of atoms. But we've been told now we have to take an ad break, so I will return and we'll talk about substitutions straight after the break.
All right. So guys, make sure you stay tuned. You grab a little snack, you have a little something to nibble on, so you don't have to keep getting up to go to the kitchen, so you can pay attention. So, from me and Marcel, we're just going to say peace out and see you after this break. Welcome back, Mindsetters. I hope you had a nice little break, and I know you're now ready back, and you've got your pens and pads, and you're making notes. And actually, me and Marcel were sitting here, and we just said Yugen. We were a bit confused, as in we saw your spelling for biofuel, and we thought you spelled beautiful, and it's like, what? Just one of those forehead slap moments, like, oh, that's what he meant. But anyway, I actually just want to send a quick shout out to Liberty. Thank you for sponsoring the show. And Bruce, I think we're good to go.
Right.
Ready?
Great. Thanks very much, Ty. And guys, just before the ad break, I was just trying to introduce you to the other type of chemical reaction we're going to have a look at tonight, which is known as a substitution. And I was using that analogy of a soccer match. And as you've seen, even if you're a player or you watch on television, that players are able to be substituted on and off the field. In other words, we take one player off the field and we put another player onto the field. That is exactly how a substitution reaction can work in a chemical type of system as well. That we basically are swapping one type of chemical with another. And I'm going to have a look at it. We'll see how it works, and we'll look at the general equations. Then I've got an example, and we can actually see how it actually works in an example. Okay, so what we've got now in a substitution reaction is that these are reactions that involve an exchange of elements in the reactants to form products. The important thing here are the words exchange of elements. That's what we mean by this term swapping. Okay, we're going to exchange elements. So if I have a general equation and I've got A, B, and C, D, what can actually happen is that we can now swap certain parts of those reactant particles, those reactant molecules, and we can now get a new set of products. And if I just scroll down slightly, for example, A plus B and C plus D, we can actually swap around, just like I've shown here, that we can swap B and C around. We're going to end up with AC and BD. That's our general equation now for a substitution type of reaction. So if I've got AB plus CD, we'll end up with AC plus BD. And you can see now from this, the way I've drawn it up on the board, which two are going to be swapping. Okay, we could have swapped A and D around. That's no problem as well. It doesn't really matter depending on what you've got. But as long as you are able to recognize the swapping process, then it's very easy to recognize these substitution type of reactions. Let's have a look at a little example over here. And what I've got is this particular molecule over here. Now, you'll notice it's 3 carbons, and it's got this OH group. And you'll remember from grade 8, sorry, not from grade 8, from grade 10, that the OH group represents the hydroxide or hydroxy group. Okay, and I'm going to react it with a substance which everyone can see is KCl, and you'll be able to tell me it's potassium chloride. So how do I now quickly just show you how this happens? Well, guys, what I've tried to do again is to try and simulate this particular this molecule. Now, you'll notice that with the models that I'm using, that the sort of shape is quite different to the way we write it down on a flat surface. So if you have a look over here, there's my carbon here in this little black sphere. 1, 2, 3 carbons. There are the 3 hydrogens associated with it. 1, 2, 3. This guy in the middle, the 1, 2. And over here we've got 2 hydrogens, 1, 2. And then the OH. Okay, this little blue sphere over here is going to represent the oxygen, and this white sphere obviously is going to represent our hydrogen. So that, guys, is my hydroxide, or what we call the hydroxy group. Over here, I've got potassium chloride. Okay, now, what have I got here? I've got a little round sphere. Okay, I've represented the chlorine, okay, with this large yellow sphere. And unfortunately, I ran out of colors, so I've had to unfortunately use another white sphere to represent my potassium. But what's going to happen now is that we're going to get the swap. So if I hold it in the sort of same position, what's going to happen now is that the hydroxy or hydroxide is going to swap with the chlorine. So what I'm going to do now is break this off. Okay, there it goes off. And the chlorine comes on, so I just simply grab it and I just attach it carefully onto there. It always takes a bit of a push. Can you see now? I've got the chlorine on there, and this hydrogen has come on like that. Okay, and what have we got? Let's get my pen. Whoops, don't need that. And I bring it down, and can you see now? I've got my KOH. Okay, there's my OH part over there. Let's put this down for the moment. There's my OH part. That I said had to represent my K. There's my potassium. Okay, my potassium hydroxide. And this now, can you see, guys, has got the chlorine on. And there's the chlorine. Whoops, let's get my pen color back. There we go. That represents my chlorine. There's my swap. There's the OH on there. So what I end up with is potassium hydroxide. And that, guys, is the significant way in which we are able to demonstrate this substitution type reaction. As I've put you on the board, can you see now that the OH and the Cl have swapped around, and hence we have a substitution reaction? So if we write it out in its molecular form in a chemical equation, let's have a look. There it is, C3H7OH plus KCl will give me C3H7Cl plus KOH. Guys, does it fit that particular style that we had? Yes, it does, because that will be AB, that will be CD, okay? This will be AC, and this will be BD. And there, guys, you can see now, if I apply my general equation, it works absolutely perfectly. So there, guys, is how you are able to recognize a swapping reaction, or what we call a substitution reaction. Okay. Ty, anything coming through at this stage?
Not
well, the
quite
guy's
yet.
quite quiet, huh?
Yeah, this page is still quite quiet. I'm still waiting for them, and I'm collecting them for you. So I'm just like, okay, I'm going to get to that question. I'm going to get to that question. I'm going to label that one. Okay, right. Then when we have the right timing, then I'll tell you, yeah.
Okay, cool. Then I'm going to get on to our last type of reaction for tonight, and that is called an elimination reaction. And we're going to we'll start it off, and let's see how far we go. I know we've got an ad break that will come up just now, and if we haven't finished, that's no problem. We'll continue after the ad break, but I think we must look quickly at our next type of reaction, which is known as an elimination reaction. Now, guys, what does the word elimination mean to you? And I'm sure a lot of you guys are sitting at home and saying, well, elimination means to remove. And that's exactly what we mean by an elimination reaction. These are reactions where a reactant is broken up into its two products. Okay. And in other words, we now are eliminating, we're removing from a molecule. So if we have a molecule A, okay, what we are doing is removing something from that molecule. So in other words, we are now going from A to form B plus C. And you might say, but hang on, that looks like it's the opposite of addition. And that's exactly correct. An elimination reaction is the direct reverse or opposite reaction to addition. Okay, addition, we were adding, so we had two reactants forming one product. Elimination now takes a reactant and we break it up into two individual products. Okay, and I'm going to have a look at an example over here. And this is a dehydration of an alcohol. Okay, so if I put my ethanol, you might remember that from our earlier reaction. If that's my chemical structure for ethanol, what can happen is that the OH and the H, in other words, the OH attached to that carbon and a hydrogen attached to that carbon, can be eliminated through some form of chemical means. And what happens is that we now form two products. Do you see that? There's the one product. Notice, guys, we've gone back to the double bond. Because if I break that off there, and I break that off there, what actually happens is that a double bond, well, that didn't work out very nicely. Let me just rub that out. Let's get back there. Notice, guys, that the double bond now reforms at that point. Didn't I say it was the opposite of an addition? Addition, what we used, broke a double bond to form a new product. Now we are taking this reactant and we're now eliminating to reform the double bond. So there now is the A part, and here now are my two products, which are B and C. Now, what's important there, again, is to look at the example. C2H4OH gives you C2H4 plus H2O. And there, guys, we can now see we have our elimination type reaction. Okay. I just think there's a little area here. That should be C5, eh? There we go. Sorry, just make a little amendment there. And therefore, we lose a hydrogen there. We take away the OH. So there we're now losing the hydrogen. And there now is the water that's been produced. Okay. I'm going to show you another example now. And I'm not going to do it on the board, but I'm going to do it with my molecules. And that is, if we go back to, let's put this over here so it doesn't roll away. if we go back to our molecule over there, this was, you'll remember, was our addition product, okay? And our addition product had the 2 bromines. Now, if elimination is the opposite of addition, then through some chemical means, I can then remove my 2 bromines. And what I do is simply break the 1 bromine off there, break that bromine off there, join up the bond to make my double bond. There it is. Here's my bromines. And can you see now, I've gone back to my 2 original molecules. So that, guys, is just showing you very quickly, is our elimination type reaction. Okay. I see
Bruce,
we've got, a calculator jumped up there. Didn't really need that. Yes,
I
time.
think I might have just found a couple now.
Right.
So,
go for
yes,
it.
and some of these are just more trying to find clarification.
Okay.
So, Ntando asked the question, she wanted to find out, I'm assuming it's a she, I'm not sure, don't shoot me, but she wanted to find out, what do you call the reaction of alkalines and halogen?
Sorry?
What do you call the reaction of alkalines and halogens?
Alkalines and halogens.
Yes.
I think she's probably talking about the word alkanes.
Alkanes.
Is it alkanes?
Alkanes,
Aha.
sorry. Yes.
Okay. Now, I'm just wondering, is she a grade 11 or grade 12, does she say?
I think grade 11.
Grade 11. Okay, so maybe they've done that in grade 11. If there are grade 11s out there who may have actually done the organic chemistry section, or maybe your teachers have given you a little bit of extra information, the question is, what do we call the reaction between an alkane and a halogen? Now, an alkane is a single bonded hydrocarbon. Okay. The other thing I'm going to ask Ty, is it alkane or alkene? Can you just check if she's asked for an alkane or alkene? Because the words are very similar, and I just want to get the spelling correct for you.
Yeah.
It's alkene.
Alkene.
Yeah.
Okay. Right. I'm going to just quickly do this over here. So we have a thing called let's get my pen. An alkene, okay, plus a halogen. Okay. Now, for the guys sitting at home, and this might be a little technical for you, but if you are able to follow, please do. An alkene is simply an organic molecule that has got a double bond in it, just like I showed in the example with the addition. In fact, I used an alkene in that example. And I'm going to now use a halogen. Okay? Now, halogen, for example, was something like bromine, it could be chlorine, it could be fluorine, it could be iodine. Any of those are going to be halogens. Okay, guys, please remember, halogens are diatomic molecules. Okay, the simplest form of those structures, okay, contain 2 atoms, making it a molecular structure. Okay, we cannot just get Br by itself or Cl by itself in the unbonded form. Okay, now, if we add an alkene with an halogen, very simply, what do we get? Well, let's extend the page. We get a reaction called a halogenation. It's called a halogenation reaction. Okay, so where does the word come from? It's quite simple. Adding addition of a halogen is called a halogenation. But if you got what I had over here, where I had my halogenation, my molecule, and I took the halogens out, in other words, I removed them to get my 2 products, that's what we call a dehalogenation. A dehalogenation. Now, you might say, well, are they related? Well, yes, they are, because this one would be an addition, okay? And the opposite of halogenation, dehalogenation, as I said earlier, will be an elimination. Whoops. There's an elimination type reaction. So guys, if you have come across these terms, that's great. Halogenation, dehalogenation, one's addition, one's elimination. I think that answers the question there.
I think, yeah. Marcel actually found another question, so he's actually going to read it out.
Well done, Marcel.
Okay, on addition reactions, are we able to use triple bonds on the reaction?
Yes, we are able to use triple bonds. Let me just extend the page a little bit. Come here. Here we go. Extend. So if I had a triple bonded structure, and I had that, okay? Now, those are called alkynes, okay? you've got an alkyne like that. All right? Alkyne means we've got 3 bonds, a triple bonded structure in the carbon. And if I add, for example, bromine again, what can happen now, guys, is actually quite important, because now we've got 3 bonds. 2 of those bonds are able to break. So what we are able to get is an addition reaction, okay? And I'll do it step by step. So the 1 will be like this, okay? So there's the bromine that breaks 1 of the triple bonds, leaving a double bond, okay? So that's going to be step 1. And then, if I can get this to extend, we're going to have, I don't want it to extend so much, so I'll just bring it up a little bit like this. You get to a step 2, where the second bond is now breaks, and we've got our original 2 bromines like that, okay, and we get another 2 bromines coming on like this, okay, and you're going to have your bonds on either side. So can you see now that if you've got a triple bond, you can actually put 4 bromine atoms around those carbons, 2 on one carbon and 2 on the other, which means, guys, if I go back up here, we are going to need 2 of those bromines to make it balance, okay? Because 2 bromines, 2 diatomic bromines, gives us 4 bromine atoms, which can then react with the triple bond. So what's nice about that question is showing you now that our chemistry can be quite varied. It's still addition. We haven't changed anything at the moment. It's still addition. We've still got the same basics as we had before, except now you've got 2 bonds that can break, and we can now put 1, 2, 3, 4 atoms onto the carbons. I think that will answer it, Marcel. Hopefully that will answer the question.
I think so, yeah.
Okay.
I think that's about it for now.
Okay, are we going to take a break, or are we going to...
I think so. We'll take a little bit of an ad break, make sure they
Okay.
have a little bit of time to get more of those questions in.
Get more questions in. That'll be great.
Exactly.
Awesome.
So guys, you know the drill. Make sure you have your pens, pads out, and you guys are writing notes. Make sure you stay tuned, and we'll see you after this break. Welcome back, Mindsetters. So I have me and my friend here, Marcel, Mr. 10,000 himself in studio. And guys, we're having fun. Guys, keep sending us your questions. Keep sending us anything you're lost with, anything. Like, send it to us. If you just want to say hi to him, come on, just say hi to him. But guys, for now, I hope you guys are ready for this next session. We're going to be answering a lot of your questions. So as I keep saying, send them in. We want them all. So for now, I think, Bruce, good to go?
Yeah, what I'm going to do
Right.
at the moment now, Ty, is that I'm going to do a quick recap of the 3 reaction types that we've actually looked at. We looked at our acid-base reactions in our program 3 weeks ago. Last week we looked at our redox reactions, and today we've looked at the reactions of addition, elimination, and substitution. Okay, so just for a quick moment while we're trying to source out our questions and things, I'm going to run through quickly our first lot of reactions. Whoops, I think our pen's now playing up a little bit there. Let's get it back. And we're going to look at acid-base as a recap. And you'll remember, if I just put this very simple reaction up, HCl plus H2O will give me H3O plus Cl minus. Well, remember, guys, that when we did acid-base reactions 3 weeks ago, we spoke about the Bronsted-Lowry theory, or the Bronsted-Lowry definitions of acids and bases, the modern theory of acids and bases. And if I ask the question, what do you understand by an acid, and what do you understand by a base, hopefully you'll be able to tell me that an acid is a proton donor, while a base is a proton acceptor. And therefore, when we look at this reaction over here, we are able to see movement of protons. And we must remember that the proton is the movement of hydrogen ions in that chemical reaction. So, can you see now, guys, that this hydrogen over here, and let's get a little color involved, this hydrogen over there, okay, that, guys, has been lost by that molecule. So, therefore, this guy is acting as an acid, okay, because he's lost a proton. And what's happened over here, H2O has gone to H3O plus, so this guy obviously has gained that proton. That proton has added itself to the water molecule, so therefore this must be acting as my base. So there we can identify now my acid and my base in the actual reaction itself. But then we also looked at something called acid-base pairs, and we were able to look at these pairs here, and we said, okay, if we've got this thing acting as an acid, okay, and if we had to look at a back reaction like that, if we had to go backwards, we can see now that what's left over from that, the Cl minus, would be gaining a proton, so it's a proton acceptor, so that will act as a base in the back reaction, and therefore we were able to link up what we call conjugate acid-base pairs, and that became known as the conjugate base of that acid. And there now is my first acid-base pair. This guy is acting as a base, so I'm going to call him B2, okay, because it's for my second acid-base pair, and in the forward reaction he's acting as a base, but if he went backwards, can you see, guys, he'd be losing a hydrogen, so therefore he's acting as an acid, and therefore we had now is our second acid-base pair. So two important things, guys, from acid and bases from 3 weeks ago. First of all, our definition of what an acid and base is, okay, and secondly, being able to identify in the reaction what are known as acid-base pairs. Having a look at what's losing and what's gaining, and remember, guys, with acid-base pairs, we always look at forward and the back. What's happening to the forward, what's happening in the back. And therefore, if we look at the back, you can see now that we can link up an acid and a conjugate base, a base and a conjugate acid over there. Okay. So, guys, that's the basic theory of our acid-base pairs. Any questions that come through yet?
Yes, Marcel actually found another question from Difoloane.
Right.
Don't shoot me. I'm trying.
Let me extend the page.
Marcel, take it away.
He's asking, oh, I hope it's a he or she, maybe. Can we use make use of the addition, elimination, and sub-reactions using inorganic compounds?
Yes, we can. Okay. We can make use of those particular reactions, but you'll probably find that your textbooks and notes, they talk a lot about these organic compounds, and that's why I've so concentrated on them. We certainly can, and if we have a look at this particular reaction, I'm going to take a very simple reaction. Okay? Carbon plus oxygen gives me carbon dioxide. Okay? If I burn coal, which is carbon, in the presence of oxygen, I'm going to get carbon dioxide. And if you look at that now, think about the pattern or general equation that we spoke about when we went through all three of those reactions. And if you have a look at this one over here, A plus B will give us a brand new substance, which is C. So can you see now that there is an inorganic reaction that's involving an addition? Can you see now we are adding? I have added carbon to oxygen, and we've got a brand new compound that's been formed, carbon dioxide. So absolutely, we can use it in inorganics. What about this one over here? Let's extend the page just a little bit more. And I'm going to put this one up. Okay. If I have a look at this one over here, and I'm just going to balance it, I'm going to need a 2 there, I'm going to need a 3 there, and a 2 there. Okay? If I look at that reaction, okay, it's a reaction that you might have looked at in grade 10, which is the decomposition reaction of potassium chlorate. Okay? Now, potassium chlorate provides us with oxygen, and when we decompose it, we actually get the presence of oxygen that is now evolved. And it's a very nice reaction that allows us to produce oxygen, and we can use that oxygen to do a variety of tests. But if we have a look at this reaction, can we see the format that we've got? A goes to B plus C. Can we see now that we have got an elimination? Do you see that? It's an elimination. Okay? It's an elimination type reaction. So yes, that's an inorganic reaction. So we've got an addition and an elimination. But what about other type of reactions? Can we get an inorganic substitution? Absolutely. We can get an inorganic substitution. And I'm going to put one up on the board now. And this one, I'm going to try this one. Let's see if it works. And we're going to get, whoopsie. Okay, now let's have a look. Well, what have we got? Well, can you see now that we've got copper plus zinc sulfate gives us copper sulfate plus zinc. What have we done? We have swapped the sulfate, okay, from the zinc, from the zinc to the copper to form copper sulfate, and we've left zinc out on its own. So that is an example, one example of a substitution. Okay. Or we can look at this one, silver nitrate, okay, plus potassium chloride will give us silver chloride plus potassium nitrate. Okay, that is another type of substitution. Okay, now if we look at this one, can you see this is a more classic type of substitution reaction than I showed you earlier. This one just showed one, where are we going? Just showed the one swapping, which was the sulfate, swapping with the, from the zinc to the copper. This one, which is a chemical reaction that is very popular and it's used as a test for the presence of chlorides, is basically taking the nitrate and the chlorine, okay, and can you see what we're doing with them? We are swapping them around. So in other words, the chlorine, or the chloride, now joins up with the silver, and the nitrate has now joined up with the potassium. So what have we got here? We've got AB plus BC is giving us AC plus BD. And can we see now that that is our classic substitution? Our classic substitution reaction. So guys, very easily, we can have a look at inorganic reactions as well. And I hope that your teachers at school, when you do this section, or if you've done this section, have been able to show you both types of reactions, with organic and inorganic, and be able to see the pattern that's emerging. And if you can follow a chemical reaction and watch the pattern, you'll be able to pick up exactly whether we got a substitution, addition, or elimination type reaction. I think that covers that question.
Right. So, Bruce, now we have a little bit of a dilemma. There's
Right.
two questions that need to be answered right
Cool.
now. There's one from Matipa. She wanted to find out how do we write the structural formula for a PVC chain, and then there's another request on if you could do a titration example for them as well.
Okay, that's pretty much out of the sphere that we've got at this stage. The titrations, which certain schools do in acids and bases, okay, that takes a bit of time. I don't think we've got the time for that. And the PVC chain is actually an addition, and I'm going to quickly have a look at that one. I know we're a little bit short on time, but I'll see how far we can get before we get told to end. And if we look at PVC, a lot of you guys will probably recognize or maybe know it as polyvinyl chloride. And what it is a polymer, but it involves an addition type reaction. It's quite a complex mechanism, and I don't want to get into that. But if we have a look at it, and we have a look at what we call the vinyl chloride monomer, looks something like this. Okay, you'll see a double bond and you'll see a chlorine like this, and what actually happens is that through this particular process called polymerization, we have an addition reaction. So what we can have is basically the adding of, I'm just going to quickly put them on like this. I don't want to waste too much time. Remember, we've got 4 bonds. Well, in fact, that's what we call an initiator, but I'm going to not get into that detail. But can you see now that we are able to look at 1, 2, 3, and so it goes on, and we can make a huge chain. Okay, but can you see now what I'm doing? I'm adding, each time, each step, I'm adding on a new vinyl chloride molecule. But you'll notice, guys, what's happening over here. Notice the double bond is not present. The double bond has gone. Again, classic addition when it comes to organic molecules. That double bond is a very reactive site, and therefore it's going to be part of the whole thing. And that helps, in this particular example, it helps the adding on of the vinyl chloride unit on, and what will happen is this chain will grow as more and more and more and more vinyl chlorides are added on. Okay, it's called a polymerization. It's an addition polymerization. It is in the grade 12 organic syllabus. It's quite complex. I don't want to go into too much detail, so I'll probably just leave it there, and hopefully that'll help that question.
All right. So I think we're good to go.
Good. I think we're done. Great.
All right. So guys, I hope you guys had fun, as me and my friend Marcel had fun here. Unfortunately, he won't be here for the grade 12 session, but I'm sure you had fun for the grade 11 session, yeah?
I had a lot of fun, yeah.
Yeah, so
interesting
you know
question.
So now he's got to figure out how he's going to go outside and pick up all the stuff he just got and take it home with him. I'm going to try to figure out if we can get some help for him as well. But from us at Mindset, I want to say thank you for being the 10,000th liker, and I hope you had fun.
I had a lot of fun. Thank you for having me.
All right. So guys, if you know Marcel and you're friends with him, hey, he's on TV. But from us guys, we're going to say goodbye and see you next time.